Hello, am I audible?
Yes, sir.
Okay. So first point, you got your timetable change. Now Friday is off, officially reserved for your project work. As such, so my lecture got shifted on Thursday, right, Sir?
Yes, sir.
Okay. So now we will follow that timetable because that is the official one. As and when I require to travel, then if it is getting clash, then and then only I will alter it. Otherwise, we will stick to that timetable only. Okay, fine. Any problem to anyone?
No, sir.
Good. So let us start. Can you see the slide?
Yes, sir.
In the last lecture up to this part, we had seen, correct? And we discussed about why COP can even reach to infinity because your delta T has to be very, very small, and that is something which is lying in your hand. As such, a self contradictory statement that the T low has to be as high as possible and T high has to be as low as possible so that the gap between them would be tending to zero and you get the COP as infinity. Up to this part we had seen. So we compared the Carnot efficiency means Carnot engine and Carnot refrigerator. Now I will take you further towards the production of low temperature. So there are different methods available with the help of which you can generate the low temperature. So basic principles and allied processes which are used for the production and of course maintenance also of the low temperatures. So these are some 6 7 different methods. Let us discuss about them in depth. So dissolution of the salts in water, this we already had seen um, with the example of sugarcane juice. Then change of phase, this is the uh, what you call sensible and latent part, latent heat transfer. So you reject the heat, temperature, pressure both remaining constant, and there will be phase change only. Then expansion of liquid with flashing. What is this flashing? Little bit I will tell afterwards. Reversible adiabatic expansion of ideal gas. This you know right from your second year SEM3 thermodynamics. Turbine, correct. And then irreversible adiabatic expansion. That is for real gases, of course, because reversible is for ideal gas. When the gas becomes a real one, it becomes a irreversible one. So that is very similar to a process called as throttling. So what is the throttling? We will discuss a little bit. We already discussed. It's a revision. Then thermoelectric cooling. This is again connected with the same Seebeck effect and Peltier effect. And then the adiabatic demagnetization. So that is the magnetic dipoles getting oriented and reoriented, etc., etc. So let us deal dissolution of the salts in water. Let's say you have certain specific salt you want to dissolve in water. And when you do so, it's a exothermic reaction, sorry, endothermic reaction. It will absorb the heat, okay? And maybe outside situation will be feeling the refrigeration effect. It can be made reverse also. It may be exothermic reaction also, and inside a liquid will get cooling effect. It will be rejected to the atmosphere. It solely depends on the type of salt which you use. Okay. Now, when let's say heating the solution, let's say the solution is now cooled down and you heat the solution, then finally you get that original salt retraced back. So this is a tedious process that you initially add it. Maybe some stirrer is required, stirring action, extra work. Because of that, it would be like a homogeneous mixture, and then heat absorption. So refrigeration effect of the water, let's call it liquid. Okay, and then you heat it, let the water get evaporated, and finally what you get as a remaining part is the salt. It is a tedious process, cumbersome way of completing the cycle, but it is one of the mechanisms through which you can generate the cooling effect So typical salts, as I mentioned over here, sodium chloride plus water. This is what we generally do for ganne ka juice. Correct? You put some ice cubes, and then on the top surface you add some salt, sodium chloride, normal salt, kitchen salt. Correct? Similarly, calcium chloride and many other salts are there. I'm just giving a couple of examples. So with sodium chloride, in such a way, you can reach up to the minimum temperature of minus 20 degrees. Change the salt, the temperature will be altered. But as we discussed, the limitation is the extraction process is very, very tedious. Every time you have to either do some mechanical work or the electrical input or the thermal input, something like that. So then ultimately the COP of the entire system would be very, very low, because to stir the salt in the liquid you need the stirrer, so mechanical work, and then you have to supply the heat, thermal energy, so as to evaporate the water and get the salt back. So it's continuously the in process. Cooling effect is the output, but the input is much more than that. So COP as such for the complete cycle would be very, very low. Okay, so that is why we generally do not go with this method. Do you agree with this? Any doubt in this method?
No, sir, no doubt.
Now change of phase. Now here you know all the standard values: 335 kilojoule per kg of water. That is for latent heat of fusion, correct? Ice part. And for the boiling, that is evaporation or reverse way, condensation, it is 2257 kg per kg. This part we had seen in our thermodynamics course also, steam table, correct? And in between, I had placed sublimation, solid to vapor, direct conversion. So here I have taken the example of CO2, and corresponding value I had mentioned over here. So directly CO2 as a solid to vapor transformation is possible. You need not go for liquid CO2, solid CO2 and CO2 gas directly. That is always possible. I think I told in the last lecture only, right? Dry ice cream shop. You can go over there and see. I had told in the last lecture only, na?
Yes, sir.
Yes, sir.
So you can go to any of the ice cream shops and see when the fresh stock comes, ice cream buckets, and all are having, all are surrounded with the dry ice, that is the solid carbon dioxide. Okay, now something related to the flashing. Let's observe this figure and let's say I start the process of expansion from here, state 1, and ending at state 2. Now what happens? Saturated liquid at pressure P1. Okay, this is saturated liquid. I hope you remember all these charts. TS chart, this is saturated liquid, this is saturated vapor, inside a dryness fraction, x1, x2, x3.
Yes, sir.
Good. So this is my saturated liquid. Okay. Now this process 1 to 2 is something similar to throttling. Throttling is isenthalpic expansion, correct? And that too for gases. Now here it is a liquid. Very basic difference. So if it is a, let's say, similar to throttling, I'm not saying exactly H1 equal to H2, but somewhat similar. So when I start expanding the liquid, the saturated liquid, so naturally inside anything is now a wet part. So it is having a vapor part as well as liquid part, and vapor part is free to expand. Do you agree?
Yes, sir.
So now this process will always show increase in entropy. S2 will be always greater than S1. It will never be isentropic one, like vertical, perfectly vertical. It will be a slant line. We know that liquid expansion is always irreversible. Gaseous expansion can be approximated to reversible, ideal gas behavior, and etc. etc. Liquid is not even compressible, so it is always a irreversible. So being the irreversible one, what I will get finally as S2 is greater than S1. So that is why the line will be always like this. It will never be like this. S2 will be never less than S1. Do you agree?
Yes.
Okay, so it is increase in the entropy S2, as just we said, greater than S1. And now since it is starting from x equal to 0, dryness fraction equal to 0 to some specific positive value of x2. Positive in the sense greater than 0. It will be never negative, greater than 0. Correct? So my dryness fraction also increases. X2 is also greater than x1. X1 is 0, saturated liquid. X2 will be having some value. So this gives me a clear picture that the part of certain liquid is, or rather, certain part of the liquid is vaporized. It is a two-phase part over here. Certain part is liquid, certain part is vapor. Now, who will be responsible for converting the liquid to the vapor? You know better that converting liquid to vapor, that means you have to add the heat. तब जाके liquid का vapor बनेगा. So who will be responsible? From where it will take that heat? So from the evaporator section, what you call it as the refrigerated space. So this is how it will absorb the heat from the refrigerated space, convert certain amount of liquid to vapor, and what you observe as a output in terms of the refrigerated space is the cooling effect. The working substance will absorb the heat. It will change its phase from 100% liquid to liquid plus vapor. And from here, the working substance will absorb the heat from the refrigerated space. So naturally, there will be rejection of heat. So that's such cooling effect. Do you agree?
Yes, sir.
Yes.
So this phenomenon, this process is called as flashing. This will never be isentropic one because it is always the reverse. Now coming back to the reversible part, isoabatic thermodynamics, same thing. Reversible adiabatic expansion of the ideal gas. So what we use is a turbine. And that is why I shift the entire process on the right hand side of the dome. That means everything in the gaseous phase on the right hand side of the dome. So this is the gaseous expansion through the turbine, or maybe even 7 piston cylinder element also. Expansion is possible. Correct? So the entire process is shifted. जैसा पहले इसमें था inside the dome, now it is outside the dome on the right hand side because it is gas. Here it is entirely liquid. Here it is two phase. Here it is gas. And since this is a reversible adiabatic, that means isentropic. So I have drawn a perfectly vertical line, no slope. I mean 90 degree only, nothing less than that. Do you agree?
Yes, sir.
And you know this basic equation right from maybe your 12th standard thermodynamics or maybe first year engineering. Okay, T2 by T1 is P2 by P1 raised to gamma minus 1 over gamma.
Sir, how is the previous process absorbing heat from the storage space?
This one,
No, the turbine one.
this one. Huh. What is the problem?
So how is it absorbing heat from the storage space basically?
Turbine is expanding, means I mean to say the air inside the turbine. Turbine is a machine and it is getting offering the expansion. If I want to maintain it at some lower temperature, then how would you execute the process? Because outside ambience is at the higher temperature, correct? Because of the expansion, there is a lower temperature. So it is free to absorb the heat from the surrounding. So surrounding temperature will be lower. Surrounding in the sense another space I'm saying. Surrounding not as the universe or atmosphere.
So the gas leaving the turbine will absorb the heat, right?
Yes, and in between
Okay.
also. If you
Okay.
cannot maintain it's a reversible adiabatic, if it is no more the adiabatic one, it will absorb the heat.
Yes, sir.
If you maintain it adiabatic, then at the end of the expansion process,
Okay.
this will be at a much lower temperature. T2 is much lower. So it
Yes,
is
sir.
free to absorb the heat from the space through which it passes. So the space through which it passes will observe the cooling effect, and the expanded air will come back to the original condition, room temperature. This is at much higher pressure. Now, after expansion, it is at some lower temperature, lower pressure. I need not change the pressure. Pressure may be whatever it is. But while it is passing through some, let's say some compartment, it will absorb the heat. The compartment will observe the cooling effect.
Understood.
Now, irreversible. It is a adiabatic one, but irreversible one. That happens for the real gases. Ideal gas होगा तो क्या होगा? Isenthalpic expansion. H1 equal to H2. If it is ideal gas, and T1 equal to T2 because H is Cp into T. So if H1 equal to H2, that means T1 equal to T2. So this would have been an isothermal line. Correct? This is the irreversible. Adiabatic but irreversible. Specifically for the real gases. So we call this process as throttling. Chapter 2. Control volume analysis. Same 3. Okay. So this is temperature versus pressure. Isenthalpic curve. Then we call this as mu Jt, daba T by daba P at constant H, and we observe that this is what is the physical actual phenomenon getting executed in your domestic refrigerator. Compressor, that is for the compression of the refrigerator, and then condenser, the heat is getting rejected, and then this comes. We call it as throttling, isenthalpic expansion. So that it would offer me lowest possible pressure, lowest possible temperature, and then it enters into the evaporator, absorbs the heat. This is how cycle gets completed. Fine.
Yes, sir.
Yes, sir.
Okay, so I hope you remember this mu Jt, then isenthalpic curve, and etc. etc. So just to make you again remember the same things, that the thermostatic expansion valve or the solenoid valve or capillary tube, whatever kind of expansion device you are using in your domestic refrigerator, please open the manual of the refrigerator, whatever model you have, company and model. Please open the manual and cross check the settings for the expansion start over here and expansion end Hello.
Yes, sir. Yes, sir. We can hear you.
Am I audible? Huh. Okay. Got
Yes,
a
sir.
call from Salman Mulani,
Yeah.
exam section. Problematic people. Fine. Can you see the slide? Or that connection got
No, sir. You
lost?
have to present again.
Ah. बरं सियर तो काय त्याला तुमच्या ह्याच्यामध्ये ऍड करा व्हॉट यू कॉल क्लास ग्रुप इज राईट नाव इन द एक्झाम सेक्शन
Yes, sir. He's always on the. He's already in the group.
he will be registered under old course pattern. He's 2014 batch student, Puran Purush. Okay, so he will be having separate course and everything separately. Just add him over here for our course. I will be adding him in the classroom, but his evaluation will be altogether different. He will not be interfering in your evaluation.
Okay, sir.
Okay, fine. So I need to present again. Is this visible?
Yes, sir. Yes, sir.
Okay. So what we are discussing is related to the setting of the thermostatic expansion valves. You need to cross check whatever refrigerant you are using. Try to find out the inversion curve for that. Okay, and try to see about the pressure settings done by the company. Very simple but interesting exercise. Say for example, your domestic refrigerator is having R134A. Then try to find out from internet this curve, inversion curve. Okay, then you will come to know about the pressure limits from the what I can say manual, operating manual, and see whether it is falling at the left hand side of the inversion curve or the right hand side. So that will assure you about the performance. Otherwise, your COP will be unnecessarily high. Sorry, lower. You can change the setting if you want. This is how practical applications of all the basics of thermodynamics, whatever you learned, come into reality. Okay. Now, the next process we already discussed for काय त्याचं नाव Peltier, Seebeck effect and Peltier effect. So both are like
Yes.
same part, vice versa. If you pass the electric current, there will be temperature gradient on either side of the material. If you generate the temperature gradient on either side of the material, then the electric current starts flowing through the circuit. So here we write down in the mathematical form Q absorbed, which is over here, okay, is pi C into I. I is the current, so nothing new in that. Pi C and similarly pi H, heat rejected. They're not related, rejected. It is pi H into I. So all both of them are the Peltier coefficients. You select the material, the Peltier coefficients are readily available. So this is how you calculate the performance. You can change the performance to maximize it or whatever it is. Okay. So in other words, I would say that this solely depends on you. Pi C and pi H are the strong functions of the corresponding temperatures, or you can say reverse way, temperatures are functions of these. So whatever the amount, you decide how much heat is to be absorbed, you decide how much temperature to be maintained over here. Accordingly, you select the material so that you get pi C and pi H as per the requirement. So this is another technique through which you can generate the cooling effect, that is thermoelectric cooling. And this is the adiabatic demagnetization, which we have seen a little bit as far as the process. Now this is a schematic. So inside a container, there is, let's say, some pre-cooling effect. So let's say liquid nitrogen bath or liquid oxygen bath, 77 Kelvin or 90 Kelvin or something like that. Then inside that is the helium, liquid helium. So you are bringing it now close to 4.2 K. And helium is the last gas in the world. तो liquefy उसके नीचे कुछ है ही नहीं. So how to bring the temperature below 4.2 K? So what you put is this kind of material. This is a salt, paramagnetic salt, whose magnetic dipoles are randomly oriented. Then you add the magnet or other magnetic effect flux. Because of that, the paramagnetic salt dipoles will get oriented, and then you remove it, and then further drop in temperature. So this is what is called as the thermal switch, connected salts. And once you apply the magnetic field, the dipoles get reoriented. If you remove the magnetic field, they again collapse, and there is a scope for the temperature inside this chamber, to fall down below 4.2 K liquid helium. So this is how you generate the temperature even lower than liquid helium, 4.2 K, 3.2 K, whatever, depending on the isotope. And this is how, depending on the strength of the magnetic field and the strength of the paramagnetic salts, you can reach to the temperature as close as possible to absolute zero. So this is that particular technique. Okay, any doubt?
No doubts. No doubts.
Very good. So here we stop with our first chapter, and I will immediately start with the second one. Any doubt to anyone for this chapter? They
No,
just
sir.
taken the review, nothing difficult in that as such. Let me start with the second chapter. Yes. This chapter also is relatively very simple because you are quite familiar with the fundamentals of thermodynamics. Is the screen visible?
Yes, sir.
Yes, sir.
Air refrigeration cycles. Reverse heat engine, air standard cycle. We know the forward cycle, now reverse cycle. Engine ka reverse, that is a refrigeration cycle. So what type of cycles we are going to study? First is the reverse Carnot cycle. Second is the reverse Joule cycle, or sometimes called as Bell-Coleman cycle. Okay, and then third part, application for cooling, how we can use it, and then some little bit numericals based on that. So refrigerator and heat pump is the concept which you are quite aware with as far as the second law of thermodynamics is concerned. Now we are using it for the air refrigeration system. I will use the basic part by making use of working substance as air. So this is one of the earliest method, very old, because air is free and abundantly available. No expensive affair. So oldest possible method. Now it is completely obsolete due to very low COP. Why low COP? Because air cannot be liquefied, cannot be in the sense, need not be liquefied for generating the refrigeration effect. So if it remains in the gaseous phase, then naturally CP is very, very low. And what is the heat transfer? MCP delta T. The CP is very low, so naturally COP is low. CP specific heat and C. Okay. So because of that, low CP value, so low COP also. And for compression and expansion process, you need huge compressors and turbines and all such kind of things. So because of that, the high operating cost. So nowadays it is restricted only for the aircraft refrigeration purposes. And why? Because it is not having any chemical refrigerant. So mass of the air is always lesser than any chemical refrigerant. So that is why the working substance mass inside the refrigeration is lower. That is why, and free available, abundantly available, not like even restricted. So that is why it is now only restricted for the aircraft applications. Nowhere else on ground applications we are using it. Now, what are the characteristics? So as we discussed first, very first, very important, throughout the cycle, The refrigerant in bracket air always remains in gaseous state. Nowhere it is changing the phase. So always sensible heat rejection, sensible heat absorption. No phase change, no latent part comes into picture. If we try to differentiate it into different ways, then air refrigeration can be split as a closed cycle and the open cycle. Now, what you can observe under closed cycle is that air as a refrigerant will be always remain inside that circuit by using pipes, connecting pipes, and the components. Whereas for the open system, the refrigerator space is actually a room which you want to cool, like aircraft cabin. That is why it is restricted for aircraft cabin. So where free air also can come, refrigerated air can come, and maybe a mixing blend depending on the percentage, whatever you require. Okay, the air expansion to the atmospheric pressure. Because it is open to the atmosphere, you have to expand it to the atmospheric pressure level. And the compressor also has to start from the atmospheric pressure. So atmospheric pressure to some high pressure for the compressor load, and for the expansion turbine load, it will be whatever high pressure to the atmosphere. This is the limitation for the open system. Whereas for the closed system, you can operate this at the pressures above the atmospheric pressure. Why your inlet pressure for the compressor could be atmospheric? No, it can be at some high value also. Because as you know, if P1 itself is higher, P2 will be further higher. So P2 by P1 ratio further higher. Raised to gamma minus 1 over gamma further higher. Of course, it will increase the compressor work, but it will give you more temperature also. So heat rejection will be more. And more the heat rejection, more will be heat absorption, opposite. So refrigeration effect also is more. So it will always be a kind of competition between more refrigeration effect desired and more compressor work which is undesired. Here there is a restriction, open system. So your pressure value is always limited near to the atmospheric pressure. Since it is open to atmosphere, it is open system, open to atmosphere. So naturally compression starts from atmospheric pressure, expansion ends at atmospheric pressure. Now what is the biggest problem with this or comparison is that since this is a closed system, even if there is any kind of leak, everything is getting operated at higher pressure. Even if there is any leak, you can detect it very easily. Here there is no such chance, and since it is open to the atmosphere, the moisture also may get inside the system, and then there is a big problem because at the time of expansion, this moisture gets frozen and blocks the passage. Here there is no such worry, I would say. You are safe because everything is a closed conduit. So safe, relatively safe, I would say. Whereas here it is every cycle it is getting exposed to the atmosphere. So the atmospheric moisture part every time susceptible to get inside the system. So the expansion may become a problematic one if the temperature after the expansion would be lower than the condensation point. Then naturally this moisture will get liquefied and then maybe even further frozen and then blocks the entire passage. Then no refrigeration effect could be observed. If the passage gets blocked, then how you will achieve anything? So that is the biggest problem for the open systems. So that is why generally not preferred. Clear with this?
Yes, sir. Yes.
Closed system versus open system. Suction to the compressor in a closed system may be at higher pressure, just we had discussed. So the size of the expansion and compression devices would be small because if you are dealing something at a higher pressure, that means the volume is very small. Dealing with the smaller volume, naturally your size reduces. Dealing with larger volumes, size will also be larger. In open system, air picks up the moisture. That is what we just discussed. Okay, and this moisture gets frozen and then chokes the valves, pipes, all the closed contents. Expansion in the open system is limited to atmospheric value. This also we discussed because it is open to the atmosphere, so I have to go for that level only. Start of compression from atmospheric level, end of expansion at atmospheric level. Whereas there is no such type of restriction for the closed system. You design the system the way you want so as to optimize or maximize the performance. Fine. Now we enter for the reverse Carnot cycle. So this is my Carnot cycle representation on a PV diagram. This is on TS diagram. I think you are much comfortable with the TS diagram. So two isothermals, two isentropic, which form like a complete square or rectangle, whatever you call it. Correct? Now, 1 to 2 adiabatic compression, perfectly vertical line. Then heat rejection. Then again adiabatic expansion, and it is reversible one, so isentropic you can see. And then isothermal expansion. So this constitutes for my complete cycle. So here you require the power, here you generate the power, here you reject the heat, here you absorb the heat. This way it completes the cycle. Such COP we already discussed. Yes. So this is lower temperature divided by delta T, T2 minus T1. Just in the last chapter only we discussed this. Correct? Fine.
Yes, sir.
The generalized form. What is my COP for the refrigerator? Output upon input, QL, lower part. Correct? Then the first law. So I will say TL divided by TH minus TL. If you go for the heat pump, desired output only changes, it would be QH. Right? Over here, it would be T2, means T high. So it would be TH divided by TH minus TL. And as such, we know about the interrelation between them that COP of a heat pump equal to COP of a refrigerator plus 1. L plus W. Correct? QH is equal to this. इसको इधर shift करो QL plus W. So heat absorbed plus the work done is equal to heat rejected. Second law. This why we take same 3.
Yes, sir.
Correct? So this part we know. And as such, the point which we discussed in the earlier chapter, you put lowest possible temperature TL equal to 0. This value. 0 Kelvin is impossible. But let's say, assume, theoretically, fictitious, it is 0. Then your COP would be 0. And highest possible temperature, that there should not be any difference between these two. They are same. Then this would be TH equal to TL. So as such, COP will be infinity. So neither 0 nor infinity are the practical cases. What I can say over here, let's say 0.001, whatever it is. And over here, some figure which is tending to infinity, not exactly infinity, tending to infinity. 10,000, 1 lakh, 10 lakh, whatever it is. Okay, so these are the limits for the performance of a refrigerator, Carnot refrigerator, of course. Okay, so COP of a refrigerator varies between 0 to infinity. And applying the same logic for the heat pump, it would be 1 to infinity. Because 0 plus 1 is 1, but infinity plus 1 means infinity 1. Right? So this is how we can recollect whatever we had learned in SEM 3 thermodynamics. And this is that funniest part of conclusion which we discussed in the last chapter only. That the cold body temperature, low temperature should be as high as possible, and hot body temperature should be as low as possible. So this is self-contradictory funniest situation or funniest requirement. Now, taking into consideration all these things, okay, any doubt to anyone?
No,
No,
sir.
sir.
Okay, now taking into consideration all these things, I want to make a practical cycle. Carnot is impossible. We know. Why?
Reversible is not possible, right?
Why not possible?
Sir, the isothermal the isothermal processes are I mean, it is difficult to achieve the isothermal processes uh, because they take a lot of space and something like that, I think.
Say for example, I have that freedom. मेरे पास बहुत पैसा है, मेरे पास बहुत जगह है. Can I make it possible?
So time ज़्यादा लगता है सर isothermal process को.
So time ज़्यादा लगता है. So
So it is very slow for it to be used in practice.
when you execute isentropic process, then it has to be fastest possible. You're not allowing the heat to be transferred. And when you execute an isothermal process, then it would be infinitely slow. So how you will design the components in such a way that at certain aspect the motor offers highest possible speed, and the other way the motor offers compression highest speed. Let's say heat rejection very slow, then again expansion highest speed, and then again heat absorption evaporator at infinitesimally slow speed. So that makes practically it is impossible. Otherwise, it is always possible. Practically, you cannot use the same motor to run the compressor and to reject the heat. To reject the heat in the piston cylinder element, you have to move the piston very, very slowly. But to compress the air inside the piston cylinder element adiabatically, you have to move the piston with infinite speed. Do you agree?
Yes, sir.
So that makes
Yes.
it is practically impossible. Correct? That is the reason. Fine. Now let us solve a couple of simple numericals to get an idea. Reverse Carnot refrigerator requires 1.3 kW per ton of refrigeration. Fine. So whatever is the tonnage capacity, for that 1 ton, I require 1.3 kW. So 1.3 kW is the compressor power. Refrigeration effect is 1 ton. You can find out the COP very easily. Do you agree?
Yes, sir.
Fine. Now it is used to maintain the region at the lower temperature of minus 38 degrees Celsius. So T low is known. COP you can calculate. So calculate TH, simple. Determine COP, calculate higher temperature, and calculate the heat delivered under COP if the same device could be used as a heat pump. Fine. So instead of QL, now I would be interested in QH. So I know the refrigeration effect, that is 1 ton. I know the compressor power, that is 1.3 kW. Add them, that is your QL, sorry, QH. Khatam. So solve it. This is COP. 1 ton, 12,660 kJ per hour. Or you can use per minute, that is 211, or per second, that is 3.5167. Whatever. Okay, and 1.3 kW, that is my compressor work. 1 ton is the refrigeration effect, so I get the COP. Is this value correct?
Yes,
Cross
sir.
check all the values. Now COP is known in terms of temperature. I know T1 divided by means T low divided by delta T, out of which T low is known to me, minus 38. I can find out T high. Is this correct?
Yes, sir.
And now the third part, heat delivered under COP if the same device is used as the heat pump. Now COP you can directly write down, this is 2.7, so it would be plus 1, so 3.7. Khatam. Now heat delivered as a heat pump is nothing but heat absorbed plus the work done. Heat absorbed, that means evaporator, work done, that means compressor. So heat absorbed refrigeration effect is 1 ton. Compressor work is 1.3 kW per ton. So you add it and you get the heat delivered. And now if you put it in the reverse way, then COP is heat delivered divided by work done. For the refrigerator, it was heat absorbed by work done. So ultimately, it should come the same value, 2.7 plus 1, 3.7. Fine.
Yes, sir.
Simple numerical. Refrigerating system works on the reverse Carnot cycle. The higher temperature in the system is 35 degrees Celsius. Lower temperature is minus 15. Low. T1, T2 दोनों दे दिए. COP very easy. Capacity is to be 12 tons. Refrigeration load is known. So I can find out the compressor power required. So COP of the refrigerator, fine. Heat rejected from the system per hour. So this is our condenser part. And the power required, that is the compressor part. So this is COP. Is this value correct? Higher value is 35. Lower value is minus 15.
Yes, sir.
Okay, now use the same COP. Refrigeration effect divided by work done on the compressor. Refrigeration effect is 12 ton given. So find out the work done. This is in kJ per hour converted into kilowatt, kJ per second. Divided by 3600, you will get kilowatt. Is this calculation correct?
Yes, sir.
Fine. Please convert it into kilowatt.
Eight 8.18.
Okay, around 8 kilowatt. Okay. So 12 TR capacity, it requires 8 kilowatt. Fine. What is second aspect missing? Heat rejected from the system per hour. Heat rejected means condenser part. So that is very similar to our heat pump. Heat rejected is heat pump, heat absorbed is refrigerator. So how would you calculate heat rejected? It is refrigeration effect plus the compressor work. Refrigeration effect directly known 12 ton. Compressor work just now you have calculated. Take care for the unit, both have to be in the same category, and then you calculate the heat rejected. Fine. 8.16.
Yes.
Cross check. Khatam. Ice is formed at 0 degrees Celsius from water at 20 degrees Celsius. इसका मीनिंग क्या है?
The heat absorbed or heat rejected by the water, the CPDT plus latent heat.
20 degrees water to 0 degrees water and 0 degree water to 0 degree ice. If you miss with the latent heat, you will end up in a miserable situation. I will show you. The temperature of the brine is minus 8 degrees Celsius. So this is lowest temperature. Find out the kg of ice per kilowatt hour. Unit is to be observed, kilowatt hour. Okay. Assume that the system operates on a reverse Carnot cycle and take latent heat as 3. ये मैं कभी नहीं दूंगा paper में. All these values must be known to you. For air and water, very standard values you are supposed to know. Okay, so let us try to deal this. What is COP? Lower temperature divided by delta T. Lower temperature is minus 8. Correct? Brine is available at minus 8. And T1 and T2. The water is at 20 degree. So this is my ice, COP. Ice temperature 0. And brine, water at 20 and brine at minus 8. Is the calculation correct? What happened?
Yes, sir. Yes, sir.
Now, why I am using this particular system heat to be extracted from the water at 20 degrees. So water 20 to water 0 and water 0 to ice 0. So this is M 1 kg Cp of water into delta T, 20 to 0, plus the latent heat. Fine. So this is I'm calculating per kg of water, whatever is the total mass. Everything is like per kg. So now you will realize that even if this would be delta T 20 degrees Celsius, but the major contributing factor out of the total answer 418 is this 335. If you miss with this, your answer is absolutely hopeless.
Sir, we are also going from 0 to -8, right?
-8 nahi. -8 is brine solution. It is the what I can say, what do you call that? Sink. मतलब -8 say it is taking that heat interaction, not directly -8. You are
System is at
maintaining the
0
ice.
ice, basically.
Zero ice. Ice is not going to further undergo the situation from 0 degree ice to -8 degree ice. You just want to generate the ice at 0 degrees Celsius. Fine.
And sir, we are assuming a constant supply of 20 degrees Celsius water, right? Because
Yes,
we have
no,
assumed COP to be constant.
nothing so specifically loudly given over there. We can assume.
Okay. Sir.
Okay, so the point to be noted over here is out of 418.6 kg per kg, major contributing factor is the latent part 335. If you miss with that, because I will never be giving this line in your paper. So if you miss with that and if you only consider about the sensible heat rejection, then there may be a problematic situation. Answer will be vague, totally vague, and evaluation would be very poor. Now 1 kilowatt hour. Okay, find out the kg of ice per kilowatt hour. What is 1 kilowatt hour? 1 kilowatt and then hour. Kilowatt means per second, and this is hour. So multiply by 3600. Correct? Second per hour. So I get 3600 kilojoules. Now this is my total capacity. This is specific capacity per kg. So take the ratio with the help of that. Correct? So m dot of ice into Cp. Cp in the sense I would say this total. Latent plus sensible. Sab mila ke. Let's say delta H. Not say Cp. Delta H. Divided by the total one. This is kg. This is kg per kg. So that will give you kg. Correct? And this is in kg. So finally you get the unitless part. So how much kg? This is missing part. Are you getting it?
Yes. Sir.
Yes, sir.
So this is the ice. 81 kg of ice you can generate per kilowatt hour. Is the calculation correct?
Yes, sir.
Okay. So we just realized the same thing. Refrigeration effect. How much refrigeration effect? Mass, let's say, of the ice, okay, into the heat removed to generate that ice. Water to ice, that is my refrigeration effect. Water at 20 degrees Celsius to ice at 0 degrees Celsius, that is my refrigeration effect. So how much it is? This much. And what is the work done per kilowatt hour? This much. And what is that equal to? COP, which I found out by knowing the temperatures. So there will always be a comparison of the COP for the Carnot cycle once in terms of temperatures and the other in terms of this basic definition, refrigeration effect and compressor work. You have to equate and find out the missing one. अगर compressor and heat rejection part दिया है, or sorry, heat absorption and compression दिया है, so then temperature would be missing. If temperature would be given, then maybe compressor work missing or something like that. So I have to find out the COP first and employ the same to find out the missing part. Out of the two definitions, COP had two definitions, one in terms of temperature, other in terms of refrigeration effect and compressor work. So one part would be given, the other part would be missing, which you are supposed to find out. And now you again can realize that instead of 418, इससे इसको minus करो. How much it would be? And then substitute it over here.
$83 something, right?
Huh? Instead of 418, you put it 418 minus 335, only sensible part.
Sir, 407 kgs of ice produced.
407. So you can see the amount of error, extent of error. So be very, very careful when you analyze the data. Whenever you come across the words from and at 0 degrees Celsius, that means sensible, latent, all these things you need to consider. Fine. Any doubt in this? How much is the time, Baba?
झाला आहे sir time.
Any doubt in this?
No sir.
Okay. So I will cover with this slide and then end up. So vapor in the reverse Carnot cycle, this is the only mechanism through which you can execute the Carnot cycle practically. Now what you have as the limitation in terms of the motor speed is that for this you require infinite speed. For this infinitely fast. Correct? Compression expansion. For this heat rejection and heat expansion has to be isothermal one, you require the infinitesimally slow speed. So instead of doing such things practically, basically impossible thing, what I do is I shift the entire cycle inside the dome. So theoretically, a liquid vapor zone, whatever you find out, if I shift the cycle inside it, then you can make it practical. So this would be a wet compression because X1 is having some dryness fraction. Here it would be saturated. Then constant pressure, constant temperature, phase change, heat transfer. Then there will be flashing of the liquid. I cannot say this as isentropic one, but let us assume it. Because this is a liquid part, liquid expansion can never be isentropic. But let's see. Somehow if I make it as isentropic one. Okay, then it would come at some particular dryness fraction again, and then further there will be heat absorption. So this will be low dryness fraction to high dryness fraction. Correct? So again, there is the limitation, practically very difficult due to the piston cylinder arrangement. But you can make it practically happen. May not be like exactly the same as Carnot, slight difference. But you can execute a Carnot cycle, or I can say 99% Carnot cycle. And the only possibility is to execute it inside the dome, two-phase dome. Here, you need not worry about the motor speed. This is constant pressure, constant temperature, phase change process. No requirement of any motor or anything, or heat rejection and heat absorption. So you require the motor only for the compression process and the expansion process. And there you maintain the infinite speed as high as possible. So here you get rid of that practical difficulty of two-speed motor, one at the lower, one at the higher. Only one motor is required at the higher speed, and for low part, there is nothing required. It is a phase change process. So this is the only exception where you can execute a practical Carnot cycle. May not be 100%, as I said, but 99% practical Carnot cycle in reality. Okay, so end up over here. Any difficulty?
No, sir.
Okay. So tomorrow we are meeting, right? And then Thursday. Now
Yes,
Friday
sir.
lecture is shifted on Thursday. Okay, fine. So should I end the meet?
Yes, sir.
Okay.
Thank you,
Thank
sir.
you.
Thank you, sir.
Thank you, sir.
Thank you, sir.